Hi everyone. So normally I'm not the type for this floating head kind of video. It's a bit too traditional video essayist for me, but specifically in this unit, as I was going over some information again, I noticed that there were a couple of things that needed a bit more time, needed a bit more context, that didn't quite belong up on the big board with everything else, so here we are. Anyway, early on in the semester, I talked about how in other math classes of mine, I like to provide extra historical context for how certain things happened, where certain things came from, because I think it helps humanize some otherwise very arcane figures to know that they didn't just appear out of nowhere because someone wanted to inconvenience you. They're the result of thousands of years of work by Arabic mathematicians trying to describe natural phenomena that would be developed by ancient Greek mathematicians, that would be developed further by continental European mathematicians, that we have developed further to our understanding now, and that hopefully will develop to a new understanding over the next few thousand years, even if none of us will be alive to see it. That it's a human process of learning, not a mystical, supernatural process of sudden discovery. But when it comes to stats, you don't quite need that humanization when so much of the stuff already exists from a real-world context, or at least a near real-world context. Sometimes I'll make up examples that aren't quite exactly in line with our existence, but they're close enough that we can talk about them in that context, and they have more of a natural connection to your everyday lives than, say, the modulus of a complex number might. And for that matter, when I'm talking about some other histories, I can look at things as coming from a whole bunch of different places, and you can connect it to a whole bunch of different kinds of people, whereas in this class, I mentioned early on as well that a lot of that would kind of just devolve down to we do this because it's what Galton said, or it's what Fisher said, or it's what Pearson said, and thou shalt not question Galton, Fisher, and Pearson on anything statistical, which isn't a very interesting conversation in and of itself without getting into context of the three of them in particular. We'll get to that later. But what we're getting into here with the normal distribution is both incredibly important information and also information that I think has a engaging story in its own right, where the ideas that we're working from here, the ideas with the normal or Gaussian distribution, started, at least according to many historians, with Abraham de Moivre in 1738 with his writing of what he called the Doctrine of Chances, where what he was trying to describe there was behaviors of things called binomial coefficients, where if you have something of form a plus b and you raise it to a power n, what he wanted to see was what happened to the terms in the middle of that expansion as you made n particularly large. And what he found was in the middle there were some oddly shaped, oddly behaving terms that actually acted in a way very similarly to stuff that we'll see with the normal distribution. Maybe not technically, because it's a little bit beyond the scope of this class, it's a little bit further into the weeds of probability theory, but he did see those, and he also had things that ended up being special cases of a result called the central limit theorem. And if that name there doesn't tell you that it's an important piece of information, don't worry, we're going to be seeing it again, and we're going to see why that matters. However, de Moivre was very much ahead of his time with this work because he was talking about things that are kind of natural and important parts of probability theory today, but this was well before this distribution had been fully described, and for that matter, well before even the idea of the standard deviation had been set into notational history. So the ideas he had here, they were very interesting, they were very involved, but they kind of languished in obscurity for a while because no one had any context for them. It wouldn't be until Laplace worked on them, beginning in 1774 and up until the 1810s, with a major publication of his in 1812 in particular, putting together these ideas towards a thing that would come to be called the central limit theorem. Like I said, it's important. It'll be coming back, where Laplace didn't call it that yet. He wasn't quite so arrogant as to make that assumption on site. It wouldn't be for another 100 years where George Polya, in particular in 1920, would give it that name. albeit in German, but what that result essentially says is if we have the right amount, the right kind of information, the right circumstances, the data that we're describing can fit into a nice, understandable, well-known pattern, or at least it can be back-ended into a nice, understandable, well-researched pattern, regardless of what pattern it naturally falls into. And, I'm skipping some details for why that matters, but believe me, as we're working through chapters 5, 6, 7, 8, and even 9, we will learn to appreciate the central limit theorem, even if, again, Laplace was still a little bit ahead of his time, because he beat the ideas of this distribution, that it really fits nicely to this pattern, by a few years as well. It wouldn't be until 1823 where Gauss would put together what he called the normal law of errors, and understand that when he was saying normal, he didn't mean that in the sense that we think of it in English. He didn't mean that as something that is expected, standard, reasonable. He meant it more in the mathematical sense, where normality is a general property that is analogous, I guess would be the best way to say it, to perpendicularity. That is, if two things are normal with respect to each other, it's kind of like being perpendicular. Again, there's more depth here than what I'm going to get into, but that's the rough idea, that when Gauss was calling these things normal, he didn't mean standard, he meant perpendicular. But this is what he was working on, where in particular he worked on a thing that would become called the Gaussian Integral, which is a very central piece of the normal distribution, hence why sometimes it's called the Gaussian distribution instead, in recognition of that particular piece of work, where over the next 100 or so years, people would finally start to see how important these results were. And it wasn't just Gauss, Laplace, and the Moivre working on these things. There were many other great mathematicians working on these things, where over that time, the term normal would start to pick up more steam as a notation for describing it, because they also had other names with this thing, talking about the Laplacian rule, or Gaussian errors, or the Gauss-Laplace integral, and it was just kind of a mess that normal would start to become more and more, well, normal. And in particular, one reference to this by Charles Sanders Peirce says that the normal is not the average or any other kind of mean of what actually occurs, but of what would, in the long run, occur under certain circumstances. Where those certain circumstances are, again, the central limit theorem. So, if there's one thing you should get out of this video in particular, it is that the central limit theorem is pretty important, because at this point I've talked about it, we've mentioned that we're going to be seeing this again for basically the rest of the semester, and 5 of the best mathematicians of the last few hundred years, along with many others behind and around them, have all recognized semi-independently and without the full context that we have now that this thing is pretty goddamn important. So, might not appreciate it just yet because I haven't actually defined properly what the central limit theorem is, but you should know we will be seeing it, and it is very, very relevant.